evening. We are going to continue what we did the other night. We just give you, okay, the basic definition of a functions, okay, and the various examples that we considered as a review. Now, what we're going to do, we can start talking about calculus, okay? So I go to my notebook and give you a preview of what it is going to be the procedure, okay, for studying the concept. So this is where we end up. Okay, remember I talk about this type of estimation that eventually would take us to the notion of the limits. Okay, and we give you various definition of a functions. So what we're going to do in calculus, as we talk about it, calculus is the study of rate of change. Rate of change of the value of the, okay, of the given functions. Now we are going to justify the method. Okay, we go with history first. So this would be 2.1. Eventually, we may be able to do up to the 2.3 tonight. Okay, and this is going to be the limit of a function. Okay, the limit of a function. We're going to estimate the value of the given function. But first, as I talked about the other night, the origin of this problem is the so-called the problem of the tangent line. So we introduce the problem of a tangent line, and then from there, we'll be able to get to the definition of the limits. We don't want to rush it, okay? So be patient. This is history. We're going to set up the concept, and then we are going to find easy method to talk about it. So this start with the famous problem of a tangent line. Okay, so what is going to be tangent line problem? So this is just preview first. Tangent line problem. Okay, so what's going to be tangent line problem? The tangent line problem would be simply you be given a curve and you want to find the equation of a tangent line to that curve. Okay, so that's the original problem. It was done by Isaac Newton first. So we'd like to find the equation. Okay, find the equation of a tangent line. Equation of a tangent line to the graph. Okay, equation of a tangent line to the graph of this function. Okay, to the graph of this function y equal to the f of x at a point. Okay, at the point with the x coordinate of a. That is originally the beginning of calculus. Okay, and we see the connection in a minute, the way we are going to connect it together. Okay, so let's see how we're going to solve this problem. So the solution is going to be, so that's the idea. You see, this is going to be xy coordinates. That is the xy coordinate. Then a curve is given to you. That's going to be a curve. The graph of a function is y equal to the f of x. And we have a point. Suppose this is going to be the point P. This is the point with the x coordinate of a. Okay, this point would have a y coordinate. If you drop it into the function, the y coordinate would be f of a. So we're going to call this point P. Okay, this is going to be the P, the point. So we have the point with the coordinate of, okay, a and f of a. So I would like to write the equation of a tangent line to the graph of the function at this point. So that was originally the first problem in calculus. Okay, any question? Now let's say I'm going to set up this problem. You want to write the equation of a tangent line, basically equation of a line. What do you need in order to be able to find the equation of a line? Any suggestion? What is the equation of a line formula? Anybody?
Y equals mx plus b.
Y equal to the mx plus b. Very good. What is m?
The slope.
The slope. Very good. So in order to write the equation of the line, we need a point and we need the slope. Okay, so we need m if you like. So the m would be the slope. So if you have these two, then we have a formula for it. Remember this is the formula. Y minus y1 equal to the m times x minus x1. So this is the equation of the line when one point and the slope is given. So that would be the target that we're going to do. Now the question is going to be how we're going to find the slope of a line. Do you remember the formula for the slope? Any suggestion? There are different ways to define the slope. One of them is the rise or run. Remember? So the formula that we know for the slope is this. So it's m equal to, you see, you need two points. M equal to the y2 minus y1 over x2 minus x1. So if you have 2 points of a given line, then we'll be able to find the slope. And if we find the slope, then we can substitute over here and get the result. Okay, so that's the plan. The point is already given to you. So the x1 is a and the y1 is f of a. So you have to find the slope. You see, at the beginning, they did have an extra problem, if you like. The extra problem at the beginning was, what is the definition of the tangent line? You see, that was the first thing that they have to discover. So they didn't know how we're going to do it. So what is a tangent line? So that was their question. Okay, any idea? Can you define a tangent line, or what's your idea of a tangent line? Let's go back to see where we see the tangent line for the first time. We see the tangent line first time in geometry. In geometry, we see it when we talk about a circle, okay? So if we have a circle, then we can define the tangent line. Now, the way they define the tangent line in a circle is this one, you see? This is the point P. So you know that this is going to be, now in a circle, it's going to be a point that's going to be touches the circle. It's going to be a line that touches the circle at this point. Now, the way they define it in geometry is this one. If you want to find the P, okay, the tangent line, so you pick another point, arbitrary point over here. Okay, so one point is given to is P, so you're going to pick a second one here. Okay, so this is going to be the second point. We call this one Q. So we have 2 points, 1, 2. Okay, then we connect them together. If we connect them together, you see this line? This is going to be a line passing through these 2 points. This line, okay, the line PQ in geometry, they call it is a secant line. Secant line. The secant line is a line that passing through 2 points. Okay, so what they do next is, now the line is intersecting the circle at 2 points. But we would like to have a line that intersects the circle at 1 point only. So what we do is we are going to move this Q towards the P. See, if you move the Q here, and if you connect them together, this is going to be a kind of, okay, this is going to be a kind of secant line that you're going to have. But if you move it closer, okay, if you move it closer, this would be, okay, the secant line. Whereas move it closer and closer, you see, closer and closer and closer. Eventually, this Q and the P would be the same as each other. As soon as the gate the same as each other, the resulted line would only intersect a circle at point P. This is going to be the tangent line. You see, this is historically the way they do it in the case of the circle. Okay. To make the screen bigger is that's it. This is the way we can do it. I think that's the best we can do. Okay. So you can do it on your own computer if you like to make this one bigger. I think this is the way I can do it because okay, so this is going to be the result that we are going to have. Okay, any question? Now let's go back to see. We are looking for the equation of this. Okay, we are looking for the equation of the tangent line. And so in the case of the circle, this is the point P that we have. Okay, so if we go back to the original one that we have, we can do the same thing over here. You see, going back to this curve. If we go back to this curve, so I'm going to write it down here. So if you want to do the same problem with the curve that is given to us, you see, that is going to be the case. So that is the given curve. You see, that's going to be the given curve. And that was the point P. That's the point P. You see, we can do the same thing. We can pick the Q here. So we have 2 points. This is P, this is going to be Q. So the coordinate of these points are going to be what? In the point P is A and F of A. And the point Q is any point we like. It's X and F of X. Okay, so this is going to be the case that we're going to have. Okay, just moving this up again. No, I can't do it. Okay, so this is going to be the point. Now, if we get our secant line, this is going to be the secant line. Now, you see in this case, since we have 2 points, we can use this formula to find the slope of a secant line. So the slope of a secant line would be what? M of PQ is going to be this quotient, Y2 minus Y1. So that gives F of X, okay, minus F of A, divided by X2 minus X1, which is going to be X minus A. So this is the slope. Okay, this is going to be is the slope. Okay, this is going to be the slope of the secant line. Of the secant line. Okay, you know that this is a kind of average velocity if you think about it as a moving object. So what we are going to do, we do the same thing that we did over here. So we are going to take this Q to be closer and closer to the P. And so this is going to be the next line that we're going to have. And then we are going to make it closer and closer. You see, as we move on, we're going to get the various time, okay? But eventually, there is going to be a situation that, okay, it's going to be the point P. There is going to be a situation that when that Q is going to be very much close to the P, this should end up with the, okay, the slope of a tangent line. So you see this is A and this is X. As you move on, getting closer and closer, look at this one. So on the x-axis, this x is getting closer and closer to the A. So if A is equal to 2, so these numbers are going to be very close to 2. Is it 2.002, 2.001? It's like you round these numbers up to the A over here. But anytime you do these numbers, you find this quotient here. So eventually, you see the tangent line, the slope of the tangent line would be approximately the slope of the secant line, okay, when the point Q getting closer and closer to the P. So with this procedure, we not only find the tangent line, but we are going to find a procedure to be able to find the slope of a tangent line. You see this, the slope that you're going to have is this. And so this means the slope of a tangent line would be approximately this quotient. You see f of x minus f of a when x over x minus a. Okay, as you can see, it's going to be closer and closer if x is going to be closer and closer to the a. So I have to go to the next page. Any question? So we estimated. It's like the rounding that we did the other night for that number. See, look at this one. The argument that we did have the other day. So there was a number over here, and with just an interval of many, many, many numbers that eventually, if you round it to the 10th place, that number happened to be 1.4. So in this case, this is going to be exactly the same thing that we have. So when we pick these Qs, so there are going to be many, many numbers. But anytime we pick a number, we are going to find this quotient. So you are going to have lots of numbers going to be closer and closer to the A, and you get lots of numbers from these quotients. So when the values of the X rounded up to the A, if you like, then these values that you're going to have over here, they are going to be rounded to a fixed number. That fixed number would be the slope of the tangent line. We write this one in the special language, if you like, and then we define it. So this is the way it was defined by the Newton for the first time. He write this type of notation. The slope of a tangent line is equal to limit of the slope of a secant line when Q getting closer and closer to the P. Now, so this means the slope of a tangent line is going to be equal to the limit of, remember this is that quotient that we created. It's going to be f of x minus f of a divided by x minus a when x goes to a. You see, that was the first time that this idea of the estimation was used in calculus. Okay, so if you think about it, this is just geometry. But if you want to do physics, in physics, this quotient over here is the average value, or it's going to be average velocity. So is f of x is going to be when you're deriving on I5, and this is going to be your, okay, your position after t hours. So this quotient over here is going to be your average velocity. But when you, okay, when you fix the A and you estimate it, in that case, it's not going to be average velocity. It's going to be velocity at the time that you want to talk about it, or at the time that you know. We call it instantaneous velocity they're going to have. Okay, so this is the first time in calculus that they realize that they are going to estimate to be able, you know, to get the result that you're going to have. Okay, any question? This is just the kind of that's going to be on. It's going to be the incentive, if you like, that we are going to put together eventually to find out that that notion of the limits it's going to be defined precise. It is not precise. This is just using the rounding idea that you're going to have. Okay, so now we have the slope of it. So this is going to be the slope. Okay, the slope of the tangent line. So when we have a slope of a tangent line, then we'll be able to find the equation of a tangent line. So I'm going to give one example, the way it was done by the Isaac Newton, and then we come back and we talk about it more. Okay, we have to take care of this estimation that we say. We have to be more precise to be able to continue. So these type of operations are going to be simplified later on, but for the time being, we have to do it. So we prepare for it. So for example, it's the first problem that was done by Newton. So he just solved this problem. Find the equation. Okay, find the equation of a tangent line. Equation of a tangent line to the graph of this function. Okay, equation of a tangent line to the graph of, okay, to the graph of what? To the graph of y equal to the x squared. Okay, y equal to the x squared at a point. It's going to be at a point with x equal to 2. So that's the original problem. Okay, so that was the original problem of the Newton. At this moment, if you want to do it, this is the method. You have to do exactly what we did over here. So this is going to be the solution. What you need a point. Okay, a point, and you need the slope to be able to do it. Point, so that's the slope, it's LO. So point is easy. X is given to you, so x is equal to 2. We substitute, we get f of 2 here. Okay, substitute, that give you y equal to 2 squared, which is equal to 4. So the point would be 2 and 4. This is the point. Now the slope. The slope, we have the formula for it. So the slope of a tangent line is, you approximate it, is the limit of the slope of a secant line. F of x minus f of a is like over x minus a. It's like the, okay, y2 minus ya. Okay, y2 minus y1 over x2 minus x1. Your a is equal to 2. So the slope of a tangent line can be approximated by this quotient. It's going to be f of x minus f of 2 over x minus 2. X goes to 2. Now we substitute. So this is going to be equal to the limit of f of x is the function, x squared. F of 2, we already got it, is 4 divided by x minus 2. X goes to 2. Okay, now we want to estimate this one. We can simplify it a little bit because the top one can be factored. So that gives you x minus 2 times x plus 2, and this would be x minus 2 when x goes to 2. You see, we're estimating. This means we're just looking for a number around the 2, not the 2. So in this case, x is not equal to 2 because we estimated. So x minus 2 is not 0, then we can simplify it. So if we simplify it, then the result would be, what is the limit of x plus 2 when x goes to 2? You see, we have to find this one. We have to estimate it. Okay, we can guess what is going to be x plus 2 when you estimate it. When x getting closer and closer to the 2, what would be the result for x plus 2? Any suggestion? if you take the value of x, which is going to be closer and closer to the 2. So what's going to be the estimate for x plus 2? What is x plus 2 approximately in that case? Any suggestion? X 4. 4 is correct. A equal to 2 is already given to. That's why I just put A. Yeah, this is going to be approximately 4, but we have to prove it. Okay, now for the time being, the way we're going to prove it, we have to estimate. So you see, this is, you round these numbers to the 2. Okay, so we have to show that if you get the numbers that are going to be closer and closer to the 2, then x plus 2 will be closer and closer to the 4. So for the time being, this is the way we are going to do it. So you have to draw a table if you like. You see, the proof for the time being is this. So this is 2. You see, this is 2. We don't care about the 2 because we are going to estimate it around the 2. So what you have to do, you have to get some numbers that are going to be closer to the 2 from the left, and some numbers which are going to be closer to the 2 from the right. And show that in that case, you are going to get the 4 that we talk about, okay? So this is the way we do it. Again, for the time being, be patient. I'm going to simplify everything. So that would be x, that would be x plus 2 that you want to estimate. So what I want to do, I'm going to estimate from this side first. So this is the number 2. So I'm going to pick the number, it's going to be less than 2. You can pick an interval for yourself. Remember, rounding to the 10th place, you want to do the rounding to the 100, etc. So what I'm going to do, I'm going to pick the numbers that are going to be between 1 and 2. That's optional. Depends on your percentage of error. So I'm not going to use the 2. So I'm going to use these numbers. You see this 1. If I drop 1 over here, this 1 and 2 would be 3. Okay, but I want to get close to the 2. So if I pick a 1.5, if I substitute here, 1.5 and 3 would be 3.5. Okay, so if I pick a 1.8, if I substitute here, that give me what? That give me 3.8. But if I get more closer and closer, so if I pick 1.9, so that give you 3.9. So if I get very close here, okay, so, I don't have a space. So if I pick 1.999, so over here, I get what? I get 3.999. Now look at this. The numbers to the right from the left, they will round up to the 2. You see, these are goes to the 2. Goes to the 2. But since I'm moving from the left, from the smaller numbers for the rounding, I'm going to call it 2 negative. 2 negative means the direction is the left. Now the numbers over here, you see, 3.5, 3.8, etc. This would round up to the 4. So the expression, the way we write it down, we say, oh, the limit of x plus 2 when x goes to 2, but from the left is equal to 4. Okay, so we show that if you estimate the values of the function from the left, okay, x getting closer and closer to the 2 from the left, those numbers would round up to the 4. Okay, any question? No, you're not done. You have to pick numbers from the other side. This is eventually it's going to be called the left limit because you did it from the left. But if you draw another table, this is going to be your x, this is going to be x plus 2. Now we are going to do the same thing, but we do it from this direction, 2 up. So I start with the 2. I'm not going to use the 2. So up, I'm going to just consider the number between 2 and 3. Again, you can pick 200, 10,000, etc. But if the number is going to be closer and closer to the 2, that gives you a better estimate. Okay, then again, pick the numbers. I'm not going to pick the 2. So get the numbers which are going to be close to the 2. Okay, close to the 2 from here. So for example, if you pick the 3, that's very bad. 3 plus 2 would be 5. You see, it would be 5. But you are not close to the 2. So you can go down. Okay, go down. If you pick something like 2.8, so it's not a good estimate. That give you 4.8. Okay, so you can come in here. Okay, if I put the 2.5, so that give me, okay, that was 2.8, 2.5, that give me 4.5. But if I get closer and closer, you see, if I pick 2.002, for example, so that give me 4.002. Then if I pick something like 2.0001, okay, so the number that I got over here is going to be what? It's going to be 4.0001. Again, you see, look at the top. If you run these numbers, okay, when they're getting closer and closer to the 2, from this direction, they goes to 2. If you run these numbers at the same time, you see the numbers in this direction goes to the 4 again. That give you the 4. So the expression they're going to use, we say that we go to the 2 from the right, 2 plus positive. So we write this one, the limit of x plus 2 when x goes to 2 positive is equal to 4. You see? I did it from the right and the left. I estimated. And I show that they are the same. So I have the 4 and I have the 4. So if you like, you can say that the limit of x plus 2, estimating x goes to 2 negative, is the same as the limit of x plus 2, x goes to 2 positive, and is equal to 4. So this means the actual estimate limit of x plus 2 when x goes to 2 is equal to 4. You see? That's the way we operate the machine of the estimation that we're going to have. So this would be the slope of the tangent line. But of course, we are going to have easy method at the end of today in order to do this type of ideas. But that's give you a better understanding that what we are talking about. Any question? So it's the idea of the estimation, it's the idea of the rounding, if you like, that we're going to do. But the one that we did the other night for the numbers, it was just on the number line. But in this case, you have a variable. You see, we have the input and the output. So if you change the input, that change will go to the to the output as well. So there are two movements, one on the x-axis or the value of the x, the other on the y-axis. So you go to the right, to the left of the 2, up and down, you go up the 4 and the down of the 4. You see in this case, 4.01, 02, etc. This is up of the 4. So it's this is what will happen, you see. So you have the 2 here, you have the 4 here. So what we did really is, in order to prove it, we get an interval around this. And this is what we did for these numbers. Then you find out that there is going to be another one here. So the situation is now any member here would have a representative here, you see. Any members here would have a representative here. So as you get closer and closer to the 2, these numbers on the y-axis go up and down, and they get closer and closer to the 4. So that's why we say that the limit of the function when x goes to 2 is equal to 4. Okay, I just did it for one interval between 1 and 2, but you can do it for any interval. You just tell me what you want, I can do it for you. Round it to the 10th, round it to the 5th, etc. Okay? So now we are in a position to give you the equation of the tangent line. Remember the point was 2 and 4 because A was 2. That's the point, 2, 4. So the point P is equal to 2, 4. And you have this slope. Write the formula. y minus y1 equal to the m times x minus x1. Substitute. This is your x1 and this is your y1. Okay, if you substitute, so that give you y minus 4 equal to the 4 times x minus 2. You have to simplify it. So that give you y minus 4. You multiply the 4 inside, it's going to be 4x minus 8. And so y would be 4x minus 8 plus 4. So y is equal to the 4x minus 4. And that gives you the equation of a tangent. Okay, the equation of the tangent line. And then do that. You see, that's history of how they arrive, and the fact that you should, you should check this one to get, to get this result. Any question so far to get the feeling of, we did it for a specific number and a specific function. So what we're going to do is we can do it for, all the functions. So that was the idea of when Isaac Newton did this one, they didn't use formulas. They just use an expression in word form. The word form is, you see for the one that we get a 4 here, they say that when x approaches 2, then x plus 2 approaches 4. They didn't use the notion of the limits. It was later on that, that those definition of the limits was, was improved, if you like. And eventually we get it right, the one that we do over here. So this basically, if you want to do those rounding that we did, so the meaning is this. Look at this one. What is the meaning of limit of x plus 2 when x goes to 2 is equal to 4? You see, the meaning is this. This means I can estimate x plus 2 by 4 as you like it. As you like it means, remember we talked about it tonight. When you do the estimate, you need a percentage of error, your tolerance. You may think about the rounding up to the 10th place, 100th place, etc. So if you tell me how close you want this to be to the 4, I can arrange it for you. Arrange it for you. You see these numbers that I pick? These numbers are picking these numbers, but I picked a special interval between 1 and 2. You may be interested in something else, so I can arrange it for you. See, look at this one. Look at this. Look at this one. So that's it. Suppose, just just give you just the way the limit would operate. It's good for you to know it. You see, suppose, as we did, limit. You see, if you are going to be a math major, this problem is not done. Okay, this problem is not done because you just guess. So the question is going to be, how do you know that your guess is correct? Okay, so this is what we continue. But in Calculus 1, we don't, precisely talk about it. But you need to know a little bit of this because if you take Calculus 3, you have to do this one all the time. Okay, look at this. Suppose x plus 2, when x goes to 2, is equal to 4. That we proved it. So then they ask you this question. The question is going to be, again, as I told you, I can show you that this x plus 2 would be round up to the 4, or I can estimate it by 4 as you like. As you like means you just give me your tolerance. How much are you prepared to lose or to gain? Remember, that would be your tolerance. So the question is going to be this. Look at this. If you are a math major, this is going to be your problem. We wanted to find the values of x so that, you see, so that the absolute value of x plus 2 minus 4 to be less than 1/10. You see that's what. What does it mean? This means you would like to round these values, x plus 2. You round it up to the 4, okay? But the percentage is 110. So if you round it up to the 10th place, you get the 4. So you have to tell us how we're going to pick those values that I put on the table for you. You see, that would be the basic job. Look at this. I can do it for you. So a little algebra here. So you say that this is it. If you have the x plus 2 minus 4 less than 110, I write this one as a 0.1. So that give me what? That give you x minus 2 to be less than 0.1. This is the absolute value, you know, that you can write down as x minus 2 between 0.1 and the negative 0.1. Then solve for x. So that give me negative 0.1 plus 2 less than x less than 0.1 plus 2. So this would be what? This is, if you subtract it, this would be 1.9. Okay, that would be 1.9. And that's going to be x. And this is going to be what? 2.1. You see, look at this. The argument that we did the other night. So this means if you pick your numbers to be between 1.9 and the 2.1, okay, then the value of f of x2 would be estimated to the 4 up to the 10th place. So that gives you x plus 2 minus 4 less than 110. So this means if you want to draw a table, to get this result, you must pick only the number between 1.9 and 1.9 and 2.1. Okay, so if you pick the numbers, you see this is going to be 1.9. This is 1.9, not the number, okay? And this is 2.1. So if you pick any number in this interval, and you drop it here, you see the value of your f of x is going to be this one. You see, look at this. And this would be, so that give you the condition here. If you check this one, again, this is going to be 4.1 if you like. And this is going to be something like, I think, 3.9. You see, so if you move in this area only, then you get this one with the estimate of the 1/10. So we can do it. If you give me 100, I do the same thing. 0.01, I create it for you. So that is why your guess is correct. It can be done for every function, but it's not easy when the function would be changed. So if you want to be very precise for the definition of this limit here, this is the way we are going to express it. Say that I can estimate x plus 2 by 4 as you wish. As you wish means you give me this percentage of error. You may say, how are you going to do it? By selecting x sufficiently close to the 2. Sufficiently close means must be in this area, you see? If x is going to be between 1.9 and 2.1. Because if you pick it in this interval, quickly you get your estimate up to the 10. If you can do this one all the time, then we say, oh, the limit of the function when x goes to 2 is equal to 4. So that's the interpretation of the limits that we use in mostly calculus 3. Because in calculus 1, we change this one into the formula and everybody would be happy and they think that, they know the definition of the limits and they are happy. But you got to be precise to be able to do it. Okay, so that was the beginning of calculus. This estimation for any function can be defined, that I'm going to define it for you, and that will take us from here. Okay, any question? So you make sure that, just get an idea of the notion of the limits. It's estimation, it's not exact. Okay, it's going to be an estimation that we're going to have. It took a mathematician quite a while, something like 50 years, to get this understanding that you see over here. Okay, if you go back and read the history of calculus. At the beginning, they accepted everything because they want to develop the theorem. But it was mathematician like, the French one, Agustin Cauchy, and eventually the German, Karl Weierstrass, was the one that created this type of ideas and we be able, to do whatever we do for the notion of the limits today. So I'm going to write this in for any function because that was just an idea for for the slope of a tangent line. And then we just keep going from there. Any question so far for the limits? Let me write down the precise definition, then we can talk about it. Please type. So from now on, you may get a couple of problems in your book that you have to do this type of estimation for us. Sometimes the numbers are already there, okay, and sometimes you pick the numbers. So be patient, just do it, but this is not the way we are going to find the limits. We are going to provide some theorems for you. Okay, so let's give you the official definition of a limit of the function. Okay, so what is the definition of the limit? So I'm going to use the same notation that I used over here, okay, for the right left. So I'm going to introduce officially this notation that we're going to use through the course. So what is the notation that we need? So if a number is given to you, if A is a fixed number, okay, is a given number, then we write. We're going to summarize everything in notation. Okay, we write x goes to a negative. You see, this notation is estimate. This notation on the top, when we estimate over or we estimate less or more. When it's a negative means from the left. Okay, so x goes to a negative means, okay, so this means x can take, okay, can take values that are less than a, okay, less than a, but close to a, That's the meaning. Okay, so you are here. You see, look at this. This is a. You're going through, getting closer and closer to the a from this direction. We don't care about the a. We are not going to use the a. Okay, so this is it. You run it from this side to get to the a. So basically, x goes to a negative means x is less than a, but x is close, okay? But x is, if you like, close to a. Okay, close from the left. Any question? Similarly, the other way around. Similarly, x goes to a positive. This means we estimate from the right. Okay, so this means, again, x can take values that are greater than a, okay, but close to a. That's it. So x goes to a positive. This is the way we write it down. This means x is greater than a and x is approximately a. See, that's the expressions. We don't care about the a, we estimate around. Okay, so this is the case. So we write, okay, we write x goes to a. This means x is approximately a. So this means if and only if x goes to a negative, x estimated from left and right, and x goes to a positive. Okay, so from now on, we are going to use these expressions. So make sure you know it. So in general, as you can see, x is not equal to a. There is maybe the situation that it is going to be, but we don't assume that. Okay, so this is the way we draw those tables. When you want to estimate it, you estimate it from the right to the left. Now, as we talk about it, if a function is given to you, you do this estimation for x, okay? You do the estimation for x, and then you get a similar one for y. So the situation is going to be, you see, the situation that we have is this one. There is a number on the x-axis. Okay, the number is a. The value of the function, the value of x is on the x-axis, going to the right, to the left. But the outputs are going to be on the y-axis. So if you go from a right and the left of the a, and you pick the numbers here and you arrive at the fixed number here, okay? That fixed number would be called L. So this L goes up and down. You see, up, down. So if you go from, you take your x from the right and the left, and you arrive at the numbers, which is going to be up and down of the L. In that case, we write this one. The limit of f of x goes to a is equal to the L. You know, it's just all, they are not formal, if you like, informal idea. So limit of f of x goes to a is equal to the L. So this means, okay, if and only if, in short, if and only if f of x would be approximately L, whenever x would be approximately a. You see, it's very informal. I'm writing it down in better form. So as you can see, your function is in between because you have the input and you have the output. So as you move the x to the a from the right to the left, as we did it for that table, then you may find out that the value of f of x is getting closer and closer to the fixed number like L. Then that would be your limits. So let me just give you the better example in the better definition. Any question? So it's all estimation so far. So if you want to write in word form, this is it. In word form for mostly calculus 3, or in general, this is how we define the limits. So suppose we have a function. Suppose the function f. The function f is defined near a number a. Near a number a means it's defined to the right and the left of the a, but not at a. If it's going to be defined at a, that's a bonus. Okay, but remember, since we estimate, we don't need to have anything when x is equal to a. So that's the idea. It's more general. So suppose f is defined. So basically, this means you don't have to have the a to be in the domain of the function. See, that's the idea. So suppose the function f is defined near a number a, and L is a fixed number again, is a number such that such that f of x, such that the values of f of x can be estimated, by L. Okay, can be estimated by L. Okay, by selecting. Okay, by selecting the values of x that are sufficiently close to A. So this means if you get closer and closer to the A, the value of your function getting closer and closer to the L. If this is going to be the case, then we write the limit of f of x when x goes to A is equal to L. You see, that's the definition, as I did it for you. So this means I run this up to the, I can make it for you, run that to the L, if as you wish. As you wish means you just tell us, how do you want to do it? Do you want to do it round up to the 10th place, 100th place, 1000th place? I can do it, and I can exactly give you an interval, you see, to be able to take care of it. If we can do this one all the time, then you say that the limit is good. So in short, the limit of f of x when x goes to A is L, okay, if and only if values of f of x can be approximately L whenever the values of x is approximately A. So that gives you the limit of the function. This is very informal. We can make it more abstract, but we do it later on. Just want to give you an idea first, and then we're going to do it to get these numbers. That is L of our example problem. No, we are out of the equation of the line that we did. You see, that was interpretation when we did the tangent line. You see, this is, if you write it down this as f of x minus f of a over x minus a, then it would be connected to the slope of a tangent. No. It's just in general. Okay, in general, whatever function you have, as you draw a table, you just go around the A, pick some numbers around the A, find the f of x, then you run that. You can estimate that the value of the function is going to be L. So L is the number that you are going to find yourself. That's going to be the one. Okay, so A would be given to you. You have to find the L. And to get that estimation, I'm going to do it. You will see it. You see, let's give you any question. So it's a rounding in two directions. You see, x is in the domain of the function. You go to the right, to the left of the A on the x-axis. On the y-axis, which is the value of the function, you go up and down of the L. So when you go to the right and the left, getting closer and closer to the A, up and down on the y-axis, you get closer and closer to the L. So you round up the value of x to the A, then you round up the value of the function to the L. If you can do it, L is going to be the limit of the function. That's an easy way to express it, of course. Okay, but it took mathematicians many, many years, okay, to arrive at the precise definition. And as we move on, I give you more information. Let's again do one example, then we simplify things. Again, be patient. We have to get the concept first. Then we give you theorems to find it. Now, let's see how we operate for the time being. Okay, so as an example, I'm going to use the example that I have the numbers for it. Look at this one. example, we wanted to find the limit. Okay, find the limit. How about this limit? Limit of x squared minus x plus 1 when x goes to 2. See, at the moment, okay? Later on, it will be simplified. You can guess what is the answer is, then draw a table to support it for the time being. Can you guess when x is going to be approximately 2, what this expression would be approximately? When it's approximately 2, what is x squared? X squared would be approximately what?
3.
3 is...
X.
Is it 4?
It's
No,
4.
no. That's it, 4. Okay, this would be 4. So this would be 4. This would be 2, and this is 1. So 4 minus 2 plus 1. Okay, 4 minus 2 plus 1. That gives you 5 minus 2, which is going to be equal to 3. Okay, so we guess that this is going to be equal to 3. But you have to support it. The support in future is going to be the proof. But for the time being, suppose means you just confirm it by a table. You just pick one interval and you show it first. Yes, it's going to be 3. So the solution is going to be, and we are going to give you a theorem, you find out. So this is going to be the limit of x squared minus x plus 1. We estimated that it's going to be equal to the 3. Okay, but we need the confirmation. The confirmation is you go to the right and the left of the 2. You pick some value which is close to the 2, and you show that this value goes to the 3. So the confirmation is this. So I pick the x. This is x squared minus x plus 1. Okay, first I want to go to the 2 from the left. So this is 2. So I have to pick some numbers here. I go between 1 and 2. Just an example. So what we have to do is we have to pick the number that's going to be close to the 2. Of course, use your calculator and find the value of the top. Okay, so if it's going to be 1, if you substitute here, see 1 minus 1 would be 0, you get 1. So get closer. The numbers that I use my calculator already, so I have them. 1/5. So if you use the 1/5 here and use the calculator, the number is, you can check it for yourself, it's going to be 1.75. Get closer. Okay, so closer would be something like 1.9. If you put the 1.9 with the calculator, so that should give you, okay, 2.71. And if you pick, if you're going to be very close, 9.995. And if you check the calculator, that give you 2.985. You see this? So as you can see, the number down the bottom, getting closer. You round this one into the 3. And the numbers that you got over here from the left, that you rounded to the 2. So this means x goes to 2. But we pick the number only from the left. So it's a 2 negative. So we can claim that the left limit, we call it, limit of x squared minus x plus 1, when x goes to 2 negative, would be round up to the 3. Okay, that's the left one. Any question? So again, for the time being, this is the way we can do it. We can estimate it. Of course, it's just a guess. You have to prove the guess later, but just wanted to see it only, okay? And you have a couple of problems in this section that you have to do it, but you're not done. You have to get something the other way around. You round it lower if you like. Then how about the upper? Okay. Any question? I have to go to the next page and explain it. I can explain it over here so we can have both of them here. Okay. So let's have another table. So this is going to be the x. And this is going to be x squared minus x plus 1. So in this direction, you have to go 2 up. 2. Go 2 up to the 3. Okay, so we circle this, make sure you are not going to use it because we estimate around the 2, not the value of 2. Okay, so I start picking some numbers in this direction. You want to get the closer and closer to the 2 from, from this direction. So the number that I have is a number close to this. I pick 2.001. 2.001. If you substitute, use your calculator, that give you 3.00. You substitute here. So that give you 3.003, which is very much close to the 3. But if you go to the right, 0.005, use your calculator, that give you 3.015. Again, it's very close. So if you pick something like 2.1, I think, 2.1, that give you 3.31. But if you get closer and closer to the 3, the situation is very, very bad. But again, we're moving in this direction. Okay, so as you can see, in this case, if x goes to 2 from the graded value, then the value of the function, again, getting closer and closer to the 3. So this means the limit of x squared minus x plus 1, when x goes to 2, but from the graded value, again, this is happened to be equal to the 3, you see? So we estimated from the right and the left, we arrive at the same number. So since we get the same number, we can claim that, you see, we say the 3 is equal to 3, means the right and the left. So this means, yes, the limit of the function, x goes to 2, is equal to 3. And you get the confirmation. Okay, this is not the proof. You see, we estimated, and for the time being, we accepted that this is going to be the result. But if you are going to be a math major, you have to prove that your guess is correct. To prove it's correct, you have to do the same thing that I did. You have to consider the difference and do those estimations. We don't do it in calculus 1. Okay, any question? So this will give you the feeling of how this is going to be operating. You may say that, oh, what is, why not? If you substitute the 2, you get the same one. You see, if you substitute the 2, that gives you 4 minus 2 plus 1. Yes, it's happened sometimes. And what is that sometimes? We are going to prove it later on. What type of function is this one? Do you remember? X squared minus x plus 1?
Polynomial.
Polynomials. We are going to prove that if we have a polynomial, the limit of the function and the exact value are the same. So this means you have a polynomial, you plug in. Okay, we plug in 2, and that gives you 3, and you're done. But you know that we are going to have various type of functions. They are not all polynomials. So that's why we need some other tools, if you like, to be able to take care of it. Okay, so, but this is just to give you some idea of how we define it. Okay, so this is the first example. Any question? Now I give you one more, and then we give you a break, and we come back, we give you a theorem, how to compute these limits. Okay, we make it easy. But we need this second example. This would be our first problem, if you like, in future, but we do it with algebra. It's a kind of piecewise defined function. You see, sometimes you may you may be given the graph of the function, not the equation of a function. So we want to make sure that if the graph is given to you, you should be able, to find the limit looking at the graph. Okay, so this would be given to you later. I'm not going to question you with the graphical one on the test because it's difficult to draw those graph. But it's nice to know. You have some problems in your book, you better check it. So let's see what is this next example. So this is going to be example. So we are going to give you a function this time, but not by the formula, by the graph only, okay? So let's see. Suppose the graph. Suppose the graph of the function, y equal to the f of x. Okay, graph of this function is given. So I'm going to draw the graph. You better wait till I finish it and then graph it. This is a very important problem, and you will see it in algebraic form by the end of tonight. You want to check to make sure that you can read the graph. So I'm going to have this part here. You see, suppose this is going to be one part of the graph. This number is going to be 2. Okay, that's going to be 2. And this number over here, okay, let's say this is going to be 2, and this is going to be, let's say, 3. Okay, that's the case. Then I'm going to move this one up. Okay, up here, I'm going to give you this graph. Okay, so when x is less than 2, this is going to be a graph. When x is greater than 2, this is going to be a graph, okay? Then I give you this number. Okay, suppose this number here is 5. Okay, so on the y-axis, I give you the numbers. This is going to be 3, and this is going to be 5. Okay, so this is going to be the case. Now I need another number. So I give you something here like 6. Okay, this is going to be 6, and then the value of the function at 6 is equal to, okay, let's say is equal to the 10 here. Okay, so this is going to be the graph. It's a piecewise defined function. You see, because we have one portion in the red, one portion for the green. And it's going to be around the 2 here. The domain is all real numbers going to the right, to the left. So we would like you to give us the following. Okay, so that's a graph. We'd like you to find each of the following. Find each of the following. Each of the following. So what do you want? We wanted to tell us what is going to be the limit of f of x when x goes to 2, but from the left to negative. And we wanted to give us what is the limit of f of x when x goes to 2 positive from the right. And then we wanted to give us what is the limit of the function when x goes to 2. And number 4, we wanted to give us what is f of 2, the value of the function. Okay, and there is going to be number 5. We wanted to find what is the limit of f of x when x goes to 6. You see? In the previous example, we did have that table, and the number, remember, we rounded up, rounded down, you get the result. But in this case, you have the function. So you can think about those numbers on the graph of the function, a similar thing, and guess what is going to be this time. Remember, the value of the x is going to be on the x-axis. The value of y is going to be on the y-axis. So on the x-axis, you go to the right, to the left. On the y-axis, you go up and down to identify those numbers. Are you ready? Now, we want to take care of the first one. Remember, x goes to 2 negative means x is less than 2. Less than 2 is here. So if you want to find the value of the function is the green one. Okay? So you see, if you pick a number here, if you want to find the value of the function, this is the way you do it. You draw a line, you intersect the graph. This is going to be the value of the function. Okay? But you want to get closer and closer to the 2. So think about it. When it's getting closer and closer to the 2, what would happen on the y-axis? What number are you going to register? See? But if I get closer and closer, look at this one. This is it. Can you guess? When x getting closer and closer to the 2, what is going to be the number on the y-axis approximately?
Is it 5?
Yeah. Some people say it's 5. 5 is correct. You see, it's like the one that we did, 1.9, 1.8, etc. As we can see, as we're getting closer and closer to the 2, because you're using only the green part. Using only the green part, you see the value of the green part is going to be down 5. Okay, so when you get closer to the 2, the number is getting closer to the 5. So in this case, this is it. So the solution is going to be for the part 1. For the part 1, the limit of f of x when x goes to 2 negative is equal to 5. Any question? See, when the table was given to we use algebra if you like to find it, but now we use geometry. Okay, are you ready for the second part? How about this one? 2 positive, this is the direction. So you have to use the red one to estimate your value. So you estimate it to what? You see?
3.
If you pick them, it's going to be 3, yes. You see? When you get down to the 2, the number that you register is going to be 3 here. So in this case, okay, so the second part, the limit of f of x, when x goes to 2 positive, that gives you 3. Okay, you have 2 portions, 2 different functions. That's why you get 2 different numbers over here. So if you want to work with the green one, that's it. You have to use only the terms. Okay, the points intersect the green part, get the 5. But look at this, you see, the numbers getting closer. Because these functions go down the 2, it's 3. The value that you register on the, okay, the value that you register on the y-axis. Any question? Now, look at this. We estimate from the left, we get the 5. From the right, we get the 3. So what's the answer to this one? You see limit of f of x, x goes to 2. Remember?
The answer
Yeah.
for this one is 5 because the 5 is filled out and the 3 isn't.
No. No, just think about it. From the left and the right, you must arrive at the same estimate. You see when x goes to 2, remember? When x equal to 2, when x goes to 2 means x is not equal to 2. So you have to get the right and the left. Left, you estimate it by 5. Right, you estimate it by 3. Since you get 2 different numbers, this means the limit does not exist. Okay? Because if you want it to be the same, you see, it's a 2 pieces. It's a 2 pieces, and then they are not going to be connected to each other. Okay? So you see when the direction is already given to you, you just go with the direction. But when x goes to 2, you see 2 is a partition point. That's a fact in calculus, wherever you are. If you want to do anything when it's a partition point, you have to consider the right and the left. Right and the left. As you can see, the right and the left, it's two different functions. It's a two different function, and you have two different numbers. If these two numbers happen to be the same, then the same number goes for number 3. Okay, so the answer to the 3, this is the way you answer it. For number 3, you say that, oh, 5 is not equal to 3. So this means the right and the left give you two different estimates. And so the limit does not exist. Limit of f of x goes to 2, does not exist. Okay, any question? On the test, don't say no solution. We put a question mark for you. You have to explain it. Okay, so they explain there are two possibilities. One of them is these two numbers the same. That same number is the limit, because they estimate from the right and the left the same thing. But if they are different, you write it down. 5 not equal to 3, so the limit does not exist. If this is 5 and this is 5, you write 5 equal to 5, so the limit is 5. Okay, so this is the way we're going to find it. This has happened only for the piecewise defined function. And most of the problems in calculus and in science are going to be of this category. Okay, any question? Ready for the next part? You see, these are estimation. We estimate the value function around the 2. But number 4 is exact value. F of 2 is algebra. F of 2, value of the function at 2. This is 2. What is f of 2? Some people, they say 5. You see, you draw the line to see where you intersect the graph. You are not going to get it from the green, from the red one, because it's empty. But if you continue, you get to the green one. It's a solid point, you see. You cannot have two solids, you know that. Otherwise, you are not going to have the graph. So in order to get the 2, we are not going to get it from the red one, but we get it from the green one. So f of 2 is 5. See? F of 2, so that's a number 4. F of 2 is 5. You see, it's interesting problem because the estimate does not exist. You see, the limit does not exist, but the value of the function at 2 does exist and is equal to 5. Any question? Of course, there is another possibility. The possibility is that, you see, if this is, they can give you the same one if it's going to be empty here. If there's going to be a hole here, in that case, you say that f of 2 is undefined, does not exist. Okay, so be careful. But when you have a solid means, you do have the equality with the green part. So that's why f of 2 is equal to 5. Any question? How about this one? What is the limit when x goes to 6? You say 6?
10.
Yes, 10, very good. You see, since 6 is not the partition point, you don't have to bother about the right and the left. Just do exactly what it is. You see, the 6 give you 10. But you got to be careful about the 2. The 2 is a partition point. Because if you go to the little bit to the right, to the left, you get two different graphs. But this is not. It's just 10. Okay, so the limit of f of x when x goes to 6 is equal to the 10. And that give you, that give an idea how we deal with this type of piecewise defined function. Any question? So we give it a break. We come back. We do everything, but we give you one theorem. We do one theorem. We call it computing theorem. Computing means you use it to compute the limits for us. The one that I did, you are not going to repeat it anymore. Okay, because we have to use theorems to be able to do it. So we repeat these problems, but with those nice tools that we're going to have, nice theorems, okay? So this part was, we're just using the preliminary result, if you like, to get an understanding of the notion of the limits. But your main job is going to be when you use those type of equation. Okay, so it's 725. Let's come back at 735, 740. Then we continue. Okay, see you then. Okay, so we're going to continue. Any question? So I'm going to give you a theorem that can be applied to do all the problems from now on, okay? So this is a part of the 2.3, and this theorem we refer to it as a computing theorem. So this means use this one to compute the limits, not the table estimation, no. So what is computing theorems? So basically, this theorem will tell you that, you see, when you're dealing with the functions, there are operations with the functions. Operations are addition, subtraction, multiplication, division, taking the square root, okay, fifth root, etc. This theorem will tell you that the notion of the limit and this operation commutes, which means if you want to find the limit of the sum of two functions, the result is sum of the limits. You find the limit of the first one, you add it to the second one. If you want to find the limit of the product of two functions, is the product of the limits. Okay, sum of the quotient, quotient of the limits. Limit of the radical, limit of the square root is the square root of the limit. Okay, so that's make it very easy for us to be able to do all our problems. So I'm going to list that. And then after that, you should be able to solve something like 15 different problems. And for the rest of the course, we are going to use it again. So there you are. So suppose two limits are given to you. Suppose the limit of the function f of x goes to a is given, is L. And we have another function. The limit of the g of x goes to a is given to you is m. Okay, then we are going to have the following. Okay, case one. Case one is addition. The limit of f of x plus the g of x when x goes to a. So if you want to find the limit of the sum of two functions, you find the limit of the first one, you add it to the second. So it's going to be equal to the limit of f of x goes to a, plus limit of g of x goes to a. The first one is L, the second one is M. That's it. So if the limit of the first one is 2, the other one is 5, 2 and 5, 7. So that gives you the limit of the sum of two functions. So this is the way we do the addition. We distribute it, if you like, the limit inside. That's the case one. Any question? Second one?
Could you
Yes.
re-explain what this is useful for? My brain got a little lost.
It's useful all the time. So if you have, if you want to find the limit of sum of two functions, so how are you going to do it? You find the limit of the first one and then the second one. That would be easier. So this means if you want to find the limit of the polynomial is what? It's x cubed plus 2x plus 5. So you find the limit of the first term, the second term, the third term. Okay?
Okay.
So that's easier for you, okay, to do it rather than doing it all together. You see? When you break it into parts, it's much, much easier to be able to do it. Okay? So as I talk about it, this commute limit of the sum is the sum of the limits. You see, that's the idea. We call it addition rule. Okay, the second one, multiplication. We multiply by a number first. If k is a number, and you will see in a minute, the application. If k is a number, then you see if k is 5, 2, 3. If you want to find the limit of the k times f of x goes to a. So your function, you see the limit of your function is 5. but you want to find the limit of 3 times the function. So what you can do is you can multiply the limit by that 3, limit by the k. So this is going to be k times limit of f of x. Okay, so this means if you multiply your function by 3, the limit of the resulted function is 3 times the previous limit, which is equal to the k times L. Okay, so if you have any coefficient, you can forget it. You see, if there is a 5 here, find the limit first, then multiply by 5. Any question? These are going to be given to you. You are going to use it in different formats, not only in this course, but also in calculus 2 and 3. So the operation is addition. The operation is, we call it a scalar multiplication. The number in calculus we refer to it as a scalar. So if there is going to be a scalar over here, you can keep it, find your limit first, then multiply it. Okay, so that will help you again. So the next one is we can use this one to get a difference. So what's going to be the limit of f of x minus g of x? X goes to a. You see, if you put the -1 here, the limit of negative f of x would be negative of the limit. So this means you can use the same thing over here, and this is going to be the difference. The limit of f of x, x goes to a, minus the limit of g of x, x goes to a. So what we did for the addition, we can have it for the subtraction. Okay, because f of x minus g of x is like f of x plus negative g of x. So this would be L minus M. So we can have the addition, subtraction. Okay, commute again, see. Limit of a difference of two functions is the difference of the limits. Limit of the sum of two functions is the sum of their limits. Okay, so that's going to be the ideal. Any question? Now the actual multiplication. If you have a limit of you want to find the limit of the product of two functions. So you can find the limit of the first one times it by the second one. It's going to be the limit of f of x, the first one, times it by the second one. We call it product rule. So it's going to be what? L times M. So again, that make it easy for you. You can break it into parts. Okay, all of them are natural. You see, naturally, this is what you expect to get these true. Okay, so that's the product, the difference, the sum. Next one is the quotient. If you want to find the limit of a quotient of two functions, see? So what you do, you go up and down. You find the limit of the top one. Limit of the top one. Okay, divided by the limit of the bottom one. You see the top one is L, the bottom one is M. Again, limit of the quotient is the quotient of the limits, you see? Quotient of the limit, the product of the limit, the difference of the limits. Okay, again, that will help us to be able to quickly find the limit of the given function. Any question? Now, the next one is the key for all the operations that we have. If you combine all of them together, you get the number 6. And you are going to use this one all the time. This one is the fact that if this function f is a polynomial, give us an example of a polynomial.
X squared plus 2x plus 3.
Okay, let's test it here. You see, if you want to find the limit of x squared, what is the other one?
Plus 2x plus 3.
2x plus 3. You see, suppose you want to find this limit. You see, if you want to find it, these are, now let's have minus 3. I want to have two different signs. You see, if you want to find this, according to the definition that we have, we can break it first because addition and subtraction. So it's going to be limit of the first one, x squared, x goes to 2, plus the limit of the 2x, x goes to 2, minus limit of 3, x goes to 2. Okay, according to the addition formula that we have. Any question? Now break it again. X squared is what? X squared is x times x. So I can use the product rule. Look at this. I can use the product rule. This is going to be limit of the x. X goes to 2 times the limit of the x. X goes to 2. Okay, here, remember there is a number here. K, I can put it out. So I'm going to plus 2 limit of x. X goes to 2. And this is just a number. So it would be unchanged. Look at this now. Limit of x, x goes to 2 is just 2. Limit of x, x goes to 2 is just 2. It's going to be plus 2 times 2 minus 3, which is the same as 2 squared plus 2 times 2 minus 3. Look at this. It's the same as plugging in. You see, if you plug x equal to 2, that gives you 2 squared plus 2 times 2 minus 3, which is what? 4 minus 3. That gives you 8 minus 3. The result would be 5. So what does it mean? This means if you have a polynomial, according to what we did over here, you see the theorems that we have, breaking it. That's why we introduced those. This means you don't have to bother about these operations. Just plug in. Only for the polynomials. Because the polynomial is going to be a combination of powers of x. So that would be, okay, any question? Give you an idea. That would be number, okay? That would be the number 6. Okay, so what would happen in number 6? The number 6 is that if, of course, we call it P of x. If a P of x is a polynomial, then the limit of P of x when x goes to a is simply P of a. And this would happen most of the time when you're dealing with the problems. Any question? So only for the polynomials, because of this, you see 1, 2, 3, 4. I just use all these in order to be able to prove the number 6. So we are not going to bothering. As soon as we identify it's a polynomial, get the substitution, and then you're done. Okay, a couple of more. Number 7, how about radical function? Okay, how about the limit of n root of f of x when x goes to a? You see, what we do with this one is the same thing that we did for the other one. You want to find the limit of the radical. If you stay outside of the radical, you are not going to get anything. So you take the limit inside. So this would be the n root of the limit of f of x, x goes to a. But you already got the inside one, so that gives you n root of that. Of course, you know that if this is going to be a square root, for example, L cannot be a negative number. In your book, they give you two cases. N is even and odd, but you don't need it. You realize it yourself. That if it's getting radical -5, So the limit does not exist. Okay, so if you want to find the limit of the radical function, take the limit inside. Take the limit inside, find it, and that give you the final answer. Okay, any question? So that's a number 7. One more. This is going to be used for the piecewise defined function. Remember the piecewise defined function, you partition around that partition points. You can find the limits if you find the right and the left limits. So the limit of f of x when x goes to a is equal to the L as we did it, if and only if the left limit of f of x goes to a negative is equal to the limit of f of x, okay, x goes to a positive, and this would be equal to L. So a piecewise defined function would have the limit if the right and the left limit are the same. So this means if they are not the same, this limit does not exist. And this is the way we are going to use it. Okay, there is one more. We talk about it later. Okay, but otherwise we are fine. We can find all the limits just using these property that we have. Okay, any question? Now I'm going to operate it. So you will see how we're going to use it, and you are going to learn by the examples how we're going to apply it, and this would be your tools for the next at least 3 weeks. Okay, and we give you one question from each on the common quiz. Okay, are you ready? So keep in mind, basically, as I told you, computing theorem. So any operation that we have, fundamental operation and the limits, they switch, they commute, if you like. Limit of the sum of the limits. Limit of the product of the limit. Limit of the quotient, limit number 6. So we use 1, 2, 3, 4 to prove the number 6, which is important. Limit of a polynomial, you just plug in. Okay, now let's do it. You need 12 problems to understand the application of this and whatever we are going to do for the time being. Okay, so I'm going to give you another one, those numbers. Okay, are you ready? Example, this is the way we're going to operate. Forget about those tables that I talk about it, those decimal number, etc. So this is the way you're going to operate using that theorem only. Okay, we would like you to find each limit. Find each limit. First one. How about the limit of x to the 5th minus 2x to the 4th minus x plus 1? X goes to negative 1. That is type 1. Let's see which of those are going to use. What type of function is this one?
Polynomial.
Polynomials. That's it. We talk about it. If you have a polynomial, it's p of x, remember? If you want to find the limit of the polynomial, just plug in. Done. You see that's number 6. If you get a polynomial, you drop the a inside and get your result. That's it. Okay, so we're not going to break it. Some people, they break this one, limit of the first time, second, etc. No, we just give you the theorem. Okay, so the solution is going to be simply, this is it, substitute. So I rewrite it. You can, you can do otherwise. This is it. X goes to negative. Substitute. Carefully use princess. Negative 1 to the 5th minus 2 times negative 1 to the 4th minus negative 1 plus 1. Simplify, give us the answer. So negative 1 to the 5th would be negative 1. Negative 1 to the 4th would be positive 1. So it's going to be negative 2 times 1. Negative, positive, that gives you plus 1 plus 1. So that gives you negative 1. This would be minus 2. 1 and 1 would be 2. You simplify these two, the final answer, negative 1. And you're done. So this is the way we find the limits. It's a polynomial, direct substitution. Give us the final answer. Any question? That's a type 1. Okay, and the way we are going to do it. Ready for the next one? Next one. The next one is a radical function. Suppose you want to do this. Limit of, okay, the limit of the cube root. Okay, it's going to be limit of the cube root of, let's say, 9x minus 1. X goes to 1. Radical function. Remember, we talked about it. If you want to find the limit of the radical, you take the limit inside. So what type of function is inside?
Polynomial.
What type? Polynomial. Direct substitution give you the result. Solution. This is it. We say the limit of cube root of 9x minus 1, x goes to 1, is the same as the cube root of the limits. Cube of root of the limit of 9x minus 1, x goes to 1. Now substitute because it's a polynomial. 9 times 1 minus 1. So that gives 9 minus 1. Okay, 9 minus 1, and 9 minus 1 is 8. Cube root of 8. What's cube root of 8?
2.
2. So 2 is the final answer. Because 2 times 2 is 4, 4 times 2 is 8. So the limit would be equal to 2, and we're done. Any question? So this is the way we take care of the radical function, okay? Polynomial radical. Any question? Now the tricky one is the next group. Very important. Let's check. The next one, number 3. The number 3 is going to be the following, the quotient function. So we have the limit of at the top is going to be 5x squared. Okay, this is going to be the 5x squared plus 6x plus 1. And the bottom is 3x plus 2. But x goes to negative 1. See this one? The rational function. Remember, to find the limit of the rational function, you have to find the limit of the top one and the limit of the bottom one. But what type of functions are the top and the bottom?
Both polynomial.
Polynomials. And we know that if you want to find the limit of the polynomials, direct substitution, they give you the result. That's it. Okay, so the solution, and this is it. I rewrite it. It's going to be limit of 5x squared plus 6x plus 1, and that's a 3x plus 2. X goes to negative 1. Substitute. 5 times a negative 1 squared plus 6 times a negative 1 plus 1. The bottom one, 3 times a negative 1 plus 2. Carefully simplify it and get the final answer. The top. Negative 1 squared is positive 1. Positive 1 times 5 would be 5. Okay, 6 times negative 1 would be negative 6 plus 1. The bottom one, negative 3 plus 2. So the top would be what? The top would be 0. It's going to be 0 on the top. On the bottom, we get the negative 1. What is 0 divided by negative 1?
0.
0. So the limit is 0. Any question? So this is the way we take care of the rational functions. Okay, we substitute, and that's it. In this case, we get 0 over negative 1. So the answer is 0, and the limit is given to you. Any question? That's a case 1. For the rational one, we are going to have 5 different cases. So let's check the other one or the other case. Any question? So let's see what is special about this group. Number 4. This 4 is different. Number 4, you want to find, okay, we want to find this limit. How about the limit of, there you are. The limit of the top is going to be something like, okay, let's have x squared minus, okay. Give you 1 minute. I want to just give you something really similar. Okay, it's going to be the same thing. So it's a 7x squared, 7x squared minus 6x minus 1 divided by x squared minus 1. And then x goes to 1. So look at this one. Let's see what is special about this. The top is a polynomial, the bottom one is a polynomial. So direct substitution should give us the answer. So directly substitute to see what's going to be the answer. Okay, solution. It's going to be equal to substitute. If you put x equal to 1, what are you going to have? It's going to be 7 times 1 is squared minus 6 times 1 minus 1. The bottom, 1 squared minus 1. Simplify it. So the top give you 7 minus 6 minus 1. The bottom one would be 1 minus 1. So the result is 0, 0. That's it. You see we get the 0, 0. So what's the answer to this one?
Wouldn't that make it undefined because you're dividing by 0?
No, it's not undefined because the top is also 0.
It means there's a common factor.
Yeah, you see, this is, you talk about this 0, 0 in algebra, etc., which is, which is wrong to create it over there to get this is going to be. You see, in calculus, we estimate, remember? We estimate when x goes to 1. It's not the precise number. So in the case of the estimation, you get this 0, 0 here, okay? So from our point of view, this would give us a message, if you like. You see this 0, 0, you may have different format. You get the 0, 0. But what we are going to do is this one. You see, you get the 0 on the top. You put x equal to 1 on the top, you get the 0. So when you get, when you substitute a number in this polynomial, and the result is 0, we say that this x equal to 1. You see, if you let the top to be equal to the 0, 7x squared minus 6x minus 1. You see, look at this one. You see, if you let this one to be equal to the 0, and if you want to solve it, you need a number that make this one 0. So if you put the x equal to 1, that would be 0, you see. If you put the x equal to 1, that would be 0. If it's going to be 0, this means x equal to 1 is zeros or the root of this equation. Okay, this is an equation, so one of the solution is 1. So when the solution is 1, remember, you get the 1. If you factor it, you need x minus 1. So that will tell you that this can be factored as x minus 1 times it by, you see the other part? This is 7x squared, so this would be 7x. 7x times x would be 7x squared, and the number is a negative 1. So negative 1 times what would be negative 1 here? Negative 1 times positive 1. You see, look at this. So if you solve this one now, that gives you x equal to 1. It's the same for the bottom one. When we get the 0, so this means if you want to solve this equation, then you have to factor it. So we get x minus 1 times x plus 1. One of the solution is 1. So when we get the 0, 0, we say this is indeterminate form. Indeterminate form means there is a solution, but I cannot find it now. I cannot determine that solution. So there is going to be a message here. The message is, you see, when you get the 0, 0, the message is this is x minus 1. You move the x to the other side. X minus 1 is the common factor of the top and the bottom. Okay, and that's why you get the 0, 0. So in order to remove the 0, 0, you have to remove the x minus 1. So as soon as we get to this 0, 0, you write it down for yourself that, oh, this means x minus 1 is a common factor. Okay, that's why we get the 0, 0. So what you do is you start it over. You start it over, so this is the given limit. We're going to factor the top and the bottom. See, but you already got one of the factors. See, that's the limit of x minus 1. And you already got the idea that x minus 1 is one of the factor. So you put the x minus 1 and the x minus 1. And then you find the other factor. You know, you can factor it using algebra, but that's easier. So the top factor is you need a 7x plus 1, and the bottom one would be x plus 1. Now the common factor, we can eliminate it. So when you eliminate it, the result would be the limit of the top 7x plus 1, and that gives you x plus 1. X goes to 1. Now we substitute. If you substitute 1, that gives you 7 plus 1, 1 plus 1. So that gives you 8 over 2, which is equal to. We do this type of idea in calculus over and over and over. So you have to pay attention to get, to get the reason. And when you get to the derivative of the function, we do it again. Okay, so 0, 0 is something for calculus, really. And we estimate it, okay? And the reason is it's an estimation to get the 0, 0 here. So we are going to have an answer for this. It's we are not going to call it undefined because you have the 0 and the 0 on the top and the bottom. Only we refer to it as an indeterminate form. This means there are infinitely many solutions. You see this one, I did it, I get the 4. If I change it, you get the 0, 0, I may get the 5, or you may get the 6. That's why we call it indeterminate form. So this means there are many, many, many solutions. Which one is it? 4 here. Okay, any question? So this is the way we're going to operate from now on. There are going to be 4 different cases for this problem. So as soon as we get the 0, 0, make sure you remember it. You see, if x goes to 1, x minus 1 is a common factor. If x goes to negative 1, x plus 1 would be common factor. And using this fact to be able, to find it quickly, rather than algebra. You know that in algebra you factor something like that, 7x squared minus 1, and just do it to get this result. Okay, any question? So this is one case that we get a 0, 0. The top is a polynomial, the bottom one is a polynomial, and we can easily factor it. That's case 1. There are 2 more cases of this. Let's do another one. Number 5. Number 5, you want to find this limit. You see, how about the limit of radical x minus 3 over x minus 9. X goes to 9. You see, this problem is a problem of the slope of a secant line. If you take the radical x, this is the same thing that we're going to use it in future. Okay, substitute. You may get it. If you substitute 9, what's going to be the result? Solution?
0, 0.
That's it. We get the radical 9 minus 3. 9 minus 9. Radical 9 is 3. 3 minus 3. 0, 0, 0. See? So, 0, 0, the message, remember? The message is there is a common factor. That common factor, x goes to 9. So the common factor is x minus 9. Okay, so you just mention it for yourself that x minus 9 is a common factor. So what you have to do, you have to go and find it and eliminate it. Now, how are we going to find it? You see this one? The x minus 9 is already done the denominator. So you have to create it on the top. To create it on the top, there is a radical expressions. So you have to remove this radical. Remember in algebra, in order to remove the radical, we multiply the top and the bottom by the conjugate of the radical expression. Remember rationalizing denominator in algebra? Rationalizing denominator means remove the radical out of the denominator. We usually multiply by the conjugate. The conjugate means this is radical x minus 3. You multiply by radical x plus 3. Okay, so that's a case 2. The case 1 is a polynomial. You can factor it right away. But here, in order to find it, you are going to rewrite it. Look at this. Original one is radical x minus 3 over x minus 9. X goes to 9. Multiply the top and the bottom by the conjugate of the top. Is the limit of x goes to 9. The top, you have the radical x minus 3 multiplied by the conjugate. The conjugate is this. So look at this, radical x plus 3. You do the same thing to the bottom. X minus 9 times it by radical x plus 3. Any question? So we must know it. As soon as we see it, we do it. Now, remember, you need x minus 9. You're not going to touch the denominator. You keep it as is. You multiply the top. It's a FOIL method, okay? But it's a special FOIL. Remember, this is this theorem that we have in identity. If you have a minus b times a plus b in algebra, that give you what? A squared minus b squared. We're using this to multiply the top. So the result is going to be radical x squared minus 3 squared. So we only operate on the top. So it's going to be equal to the limit of x goes to 9. The top would be radical x squared minus 3 squared, a special FOIL. The bottom one as is, x minus 9 times radical x plus 3. So the top one, radical x squared would be just x. So that gives you x on the top, 3 squared would be 9. You see the common factor? If you don't get it, probably you miss something. That's going to be x minus 9 times radical x plus 3. Okay, x goes to 9. Now we have the common factor. You see the common factor on the top and the bottom. Eliminate it. The left over on the top would be 1. So you end up with limit of the top is 1. The bottom one is radical x plus 3. Now substitute. X goes to 9. So that gives you 1 over radical 9 plus 3. Radical 9 would be 3. 3 plus 3 would be a 6. And you're done. You see what you did? In fact, in future, you find out that you find the slope of a tangent line to the graph of y equal to the radical x at the point with x equal to 9. Of course, in future, we have a shortcut for this type of ideas, but not now. Okay, so it's very popular techniques that you are going to use, in various places, and it's not difficult. So again, we get the 0, 0, but there is a radical here. You have to get rid of the radical. So you have to multiply by something nice. That something nice is going to be conjugate. So that would be negative always, the difference. So the radical x minus 3, you multiply the top and the bottom by radical x plus 3, the top and the bottom. You're not going to touch the bottom one because you will lose x minus 9. On the top, use this theorem. The square of the first minus the square. See, radical x times radical x Radical x squared, 3 times 3 would be 9. So you should get x minus 9 on the top and the bottom. You eliminate it. They 1 over radical x plus 3, x goes to 9, substitute 1, 6, the final answer. Any question? So these are the, the techniques that you learn through this example. We use this one later on to prove a great theorem. We call it the chain rule. So I give you another one. There is another one that there is a little bit of algebra involved. Want to make sure that you are not going to lose it, okay? So this would be a very popular case. So something similar with more algebra. What number is it? Number 6. I told you should have 12 problems. That's a 6. We have 6 more. So let's do this one and we do the rest next time. So look at this. See what is special about this one. You want to find this limit. Limit of radical 3x plus 1. Okay, minus 4. Divide by x minus 5. X goes to 5. See this one? Substitute. You may substitute, you may get it. It's not the case that always you get 0, 0. Okay? So substitute the numbers to check it. So it's going to be equal to what? Replace x by 5. So it's going to be 3 times 5 plus 1 minus 4 over 5 minus 5. Okay, the inside 3 times 5 would be 15 and 1 would be 16. Radical 16 minus 4. This is 0. So that gives you 4 minus 4. That gives you 0, 0 again. Again, the message. What's the message?
X minus 5 is a common factor.
That's it. You see, we have a common factor. Since x goes to 5, so x minus 5. It's good for you to write it down so you know what you're looking for. X minus 5 is a common factor. Common factor. Now, we have it down here. So we have to create it on the top to be able to eliminate it. It's not a polynomial to factor it, it's a radical. Since it's a radical, you multiply the top and the bottom by the conjugate. The conjugate is the first term plus 4. Okay, so we do it the other way around, or start it over. This is going to be the case. We have the original one. I have to rewrite it. Radical 3x plus 1 minus 4 over x minus 5. X goes to 5. I multiply the top and the bottom by the conjugate. So it's going to be limit of x goes to 5. So this is it. The first part is as is, 3x plus 1 minus 4. Now you multiply by the conjugate. The conjugate is this, the square root of 3x plus 1, but plus 4. Okay, the bottom one, you have x minus 5. And you have to multiply by the conjugate, the same thing. Radical 3x plus 1 plus 4. Any question? Now remember, you are looking for x minus 5. You're not going to touch the bottom one. You keep this one as is. Now use that theorem, the FOIL. You multiply, it's going to be a square of the first minus the second. You have to keep the limited all the time. So is the limit of x goes to 5. There you are. The square of the first one, you like multiplying these two together. Radical 3x plus 1, everything is squared, minus square of a second one. The bottom one as is, x minus 5, okay, times the square root of 3x plus 1 plus 4. Continue on the top, you square this one, you lose the radical. So x goes to 5. So that gives you 3x plus 1 minus 4 squared 16. The bottom one, x minus 5 times radical 3x plus 1 plus 4. Keep going. You need x minus 5 on the top. So it's the limit of x goes to 5. On the top, combine the like terms, 3x. 1 minus 16 would be negative 15. This is going to be x minus 5 times radical 3x plus 1 plus 4. Any question? We need x minus 5 on the top. We have 3x minus 15. What are we going to do to get x minus 5 here?
Factor out the 3.
We factor out the 3. You see, for this type of problems, you may have to do extra job. So, because you must get that common factor. So this would be x minus 5 as is, radical 3x plus 1 plus 4. Now pull out the 3, you get x minus 5. Any question? Common factor out. So the leftover on the top would be 3. Limit of x goes to 5. So the top is 3. The bottom one is 3x plus 1 plus 4. This is the time to substitute. You substitute x equal to 5. Since it's the end of the problem, no limits. So it's going to be 3 times 5 plus 1 plus 4 outside. So this would be 3. 3 times 5, 15. 15 and 1, 16. Plus 4. Radical 16 would be 4. 4 plus 4. 3, 8. The final answer. Done. In future, we are going to have a formula. We call it chain rule formula as we go on in next chapter. When you get the chain rule, this can be done quickly. But these techniques are very important in calculus, okay, to be able to take care of it and carry on the algebra. Okay, it's not difficult, but you have to identify that common factor at the beginning. You get the x minus 5, and eventually we get the final answer. Okay, so this is 0, 0 with the radical. There are 2 more of these 0, 0. So that's it for tonight. So we need, that's 6. We need 6 more examples to be able to do the job, and then that would take us to the quiz 1. Okay, so there are a couple of more theorems that we talk about it. So I will post your practice quiz number 1, so you can have a look at it. Okay, because you can do some of these problems that we did so far, but you have to wait to be able to finish all of them. Okay, so just do this one, get practice, because this is going to be your tools for the most of these chapter 2 and chapter 3. But we are not done. We have to have 6 more problems at least to be able to get it. Okay, any question? So study carefully and then let me know if you have any question. So we finished this one. That's a 2.3. So we finished the 2.3. We are not to talk about 2.4, but we talk about 2.5 before your quiz number 1. So we go up to the section of 2.5. That is going to be the target. But we're not going to rush it. There's going to be a practice quiz. We're going to practice on that one before I give you the actual quiz. Okay, any question? So have a good one and see you. That's it. See you next week. Bye-bye.